channel. All right, so Chemistry 111, this is the ACS final review, and we're just starting up here again at question 48. We just had a quick break. Question 48 says, if you're given a balanced chemical reaction and the amount of one reactant, determine the amount of the other reactant needed for the reaction to proceed. So if you have 45 grams of copper reacting, how many grams of aluminum oxide will you need in this reaction? Well, let's just do a little stoichiometry here. Luckily, we have a beautiful balanced equation. So if we have 45 grams of copper, since we have the molar ratios of aluminum oxide to copper, which is 3 coppers to 1 aluminum oxide, first we're going to need to determine the number of moles of copper. And we know that in 1 mole of copper, we go to the periodic table and we see that we have 63.55 grams of copper. Like that, from our balanced equation, we know that we have 3 moles of copper. And for every 3 moles of copper, we're going to need 1 mole of aluminum oxide. And we want to know the mass of aluminum oxide, and we know that for every 1 mole of aluminum oxide, and I've already gone ahead and looked up the molar mass of aluminum oxide, it's 101.96 grams of aluminum oxide. Now we can double check our units. Let's see here, grams of copper cancel, moles of copper cancel, moles of aluminum oxide cancel, and we're left over with grams of aluminum oxide. When you punch that spinach into your calculator, you can only have 2 sig figs because you're starting with the 45 grams of copper, and you end up with 24 grams of aluminum oxide as being the final answer. Number 49, if you're given a balanced chemical equation in the amount of one reactant, determine the amount of product formed. I don't like product produced, it should be product formed. That sounds a little bit better. So if we have 45 grams of copper reacting, how many grams of copper 2 oxide are going to be formed? Okay, so let's see here. We got 45 grams of copper. Same thing we did before. We know that in 1 mole of copper, we have 63.55 grams of copper. We know that for every 3 moles of copper, we're going to form 3 moles of copper 2 oxide. And we know that in 1 mole of copper 2 oxide, I've gone ahead and looked at the molar mass of copper 2 oxide. It's 79.545 grams of copper 2 oxide. Double check our units. Grams of copper cancel, moles of copper cancel, moles of copper 2 oxide cancel, and we're left over with mass of copper 2 oxide, and that gives us 56 grams of copper 2 oxide that is formed in that reaction. Number 50, given the amounts of 2 reactants, determine the amount of excess reactant left over. We already solved this problem before, didn't we? We did something almost identical to it. If we write down our balanced equation, so 3 copper plus 1 aluminum oxide produces 3 copper 2 oxide plus 2 aluminum. If I'm starting out with 0.25 moles of copper and 0.25 moles of aluminum oxide, we already decided in the last video that copper is the limiting reactant. And so we can write that down here. Cu is limiting reactant. So if 0.25 moles of copper react in blah, 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 what is the amount of excess reactant? So if we lose 0.250 moles of copper, right, we're going to be left over with 0. But we know that if we have 0.250 moles of copper and we have 3 moles of copper reacting for every 1 mole of aluminum oxide, right, we divide that by 3 and we end up with 0.0833 moles of aluminum oxide reacting. So we're going to subtract 833 moles. And then what we're going to be left over with is 0.167 moles of aluminum oxide left over. So that's how many moles are going to be in excess. Number 51, given a balanced equation, which we have right here, the combustion of a molecule called hexane, in percent yield, in amount of product formed, determine the amount of a reactant needed for the reaction. Okay, so what is the mass of hexane, C6H14, that's required to produce 589 grams of carbon dioxide? Well, keep in mind that this proceeds with a 65% yield. Okay, so if we're proceeding with a 65% yield, this is our actual yield. So what's our theoretical yield going to want to be, right? We're going to want to make much more than that, right? We're going to divide that by 0.65. So 589 divided by 0.65 gives us 906. So if we take this 589 and we divide it by 0.65, we end up with theoretical yield, which would be 906.2 grams. Now, if you're wondering, like, what the heck are you doing, Mr. Dion? What I'm doing is I'm saying, well, what's the theoretical yield? Because I know I'm not going to get this. If you take your calculator and you put in 906.2, try it, multiply it by 0.65, you end up with 589.0. Okay, so I'm going to set up my equation so that I want to make 906.2 grams of carbon dioxide. Let me show you. I'm going to want to make 906 grams of CO2, and I know that in 1 mole of CO2, I've got 44.01 grams of CO2. I know that for every 12 moles of CO2 that's formed, I'm going to consume 2 moles. I should say moles of CO2, so I'm getting ahead of myself. 12 moles of CO2. I need 2 moles of C6H14, again, which is called hexane. And I know that in 1 mole of hexane, C6H14, again, I've gone ahead and tallied up the molar mass. It's 86.18 grams of C6H14. Look at my units. Grams of carbon dioxide, moles of carbon dioxide, moles of hexane cancel, and I'm left over with the mass. So if I type that in, 906 divided by 44.01 divided by 6 times 86.18, and I end up with I can have 4 sig figs here, so I end up with 295.7 grams of C6H14. So that's how much hexane or C6H14 you'd have to start with in order to get 589 grams of carbon dioxide. Number 52. Given a chemical equation, the amount of one reactant and the amount of product formed, determine the percent yield. This is a limiting reactant problem. It says, no, sorry, it isn't. It says if 9.35 grams of aluminum, so if I take aluminum and I react it with oxygen to make aluminum oxide, which is Al2O3, okay, what is the percent yield? Well, first I have to balance this. So I have 2 here, and then I'm going to need 3 over 2 here. If I want to balance it using whole numbers, I'll multiply everything by 2. So I'd have 4, 3, and 2 as my coefficients. So what's the percent yield? So this is how much I get, right? This is my actual yield here. So I need to determine my theoretical yield in order to determine my percent yield. Well, let's work out what the theoretical yield is. So if I start with 9.35 grams of aluminum, and I know that in 1 mole of aluminum, I have 26.98 grams of aluminum. For my balanced equation, I know that for every 4 moles of aluminum, I'm going to make 2 moles of aluminum oxide. Okay, and then I want the mass of aluminum oxide, and I know that in 1 mole of aluminum oxide, and we're just tallying up the molar mass of aluminum oxide, which is 101.96 grams of aluminum oxide in a mole. check our units. Grams of aluminum, moles of aluminum cancel, moles of aluminum oxide cancel. We're left over with the mass of aluminum oxide, which is 17.7 grams. So now if I want to determine my percent yield, it's going to be actual over theoretical multiplied by 100%. Okay, so my actual is 13.2. That's what I got. My theoretical was 17.7, and I multiply that by 100%. And when you do that, you end up with 74.6%. 74.6%. All right. Next one's just conceptual. Conceptual understanding of the relationship between molar mass, number of molecules, volume of gases. So if you have two gases at the same temperature, or two molecules of a gas at the same temperature, they're going to have the same kinetic energy, same mass for the same number of moles, same mass, same number of molecules, same mass, same volume, same mass, right? Because we think of ideal gases as being dimensionless points. Let's try a problem number 54. Given volume pressure and the temperature of a gas, to solve for the number of moles, you have a 3,500 milliliter balloon at 28 degrees Celsius, has a pressure of 5.36 atmospheres. How many moles of gas are in the balloon? For that, we're going to use the formula PV is equal to nRT. We're going to solve for number of moles. Number of moles is going to be equal to PV over RT. We have our pressure in atmospheres, which is 5.36 atmospheres. We have our volume in milliliters. Divide that by 1,000 in your head, you get 3.500 liters. The gas constant 0.028206 liter atmosphere per mole Kelvin. And then our temperature 28 degrees Celsius. If we add 273 to that, we get 301 Kelvin. So 301 Kelvin, like that. Check our units. Atmospheres cancel, as do liters and Kelvin, and we're left over with the number of moles. And the number of moles in that balloon is 0.759 moles of gas. Number 55. Given a graph showing the molecular speed of various gases, determine the one with the higher molar mass. It says hint. Fat gases move slow. So the gases that are the heaviest move the slow. Right? You probably remember the formula that root mean square speed is equal to 3RT over M. So what does that tell you? That the speed is inversely proportional to molar mass. So the heavier the molecule is, or the heavier the gas is, the slower it's going to move, whether it's a molecule or an atom. Number 56, given four gases, determine which one is going to diffuse with the highest rate of diffusion. Well, remember Graham's law of diffusion, and if we compare the rate of one gas over the rate of a second gas, it's going to be proportional to the inverse of their molar masses. Redox is also really important. So oxidation is losing electrons, reduction is gaining electrons. Oxidation number, you have to know how to calculate an oxidation number. For example, what's the oxidation number in sodium bromate? So we have NaBrO3, sodium bromate. Well, sodium has a charge of +1, so we have sodium +1 to X, an oxidation of a number of 1. Then you have the bromate ion, which has a charge of -1 overall. But we know that the oxygen, right, we have 3 of those, and oxygen has a charge of -2, so that gives us -6. So that means that the bromine must be +5. So that's the oxidation number of the bromine in there. What's next? Number 59, the conceptual understanding of the relationship between specific heat and energy gain. The one with the smallest specific heat will have the highest temperature increase. So if you look at these metals, you got zinc, magnesium, right? You got iron, you got silver, and you got lead here, all their specific heats. It says if you take 25 grams of each of these, right? You start it with 25 gram sample of any of those metals. and they're all at the same initial temperature, and you apply some heat to them, which one's going to heat up the fastest? Well, think about the units. It's joules per gram degree Celsius. So if you're adding the same amount of heat, right, which one's going to heat up the fastest? It's the one that's got the lowest specific heat, right? It's going to heat up the fastest. Yeah, anyhow, and you can think of it as Q is equal to M times C times delta T. Okay, so the biggest delta T, if they all have the same Q and they all have the same mass, the delta T is going to be proportional to the inverse of specific heat. So whichever one has the smallest specific heat is going to give you the biggest change in temperature. So out of all of these, it would be lead. Yeah, sorry, the answer is down here. All right, number 60, given a potential energy curve, determine if the reaction is exothermic or endothermic. So if we have, you know, our enthalpy, that's not a very good graph, is it? Enthalpy on our y-axis, right? And this is the reaction coordinate, or just time, right? If you have your starting materials and you end up with something like that, that would be an endothermic reaction, right? And then if you have something that looks like this, that's an exothermic reaction. Anyhow, that's the only explanation I can give you with 1 minute left. Determine delta H for a reaction. So you should know what reaction corresponds to the delta H of formation of arsenic oxide. Well, remember that delta H of formation is an element, 1 mole of a compound made from its elements in their standard state. So the standard state of arsenic is solid. The standard state of oxygen is O2 gas. And that's going to give us arsenic oxide solid. Then we just have to balance it out. So you'd need 3/2 here, and you need a 2 here. So that would be the reaction for the delta H formation of arsenic oxide.